Chapter 2 Solutions. Almost all processes in the body occur in some kind of liquid solutions. Objectives. After studying this unit, you will be able to describe the formulation of the different types of solutions, express concentration of solution in different units, states and explain Henry's law and Raoult's law. Distinguish between ideal and non-ideal solutions. Explain derivations and real solutions from Raoult's law. Describe colligative properties of solutions and correlate this with molar masses of these solutes. Explain abnormal colligative properties exhibited by some solutes in solutions. In normal life, we rarely come across pure substances. Most of these are mixtures containing two or more pure substances. Their utility or importance in their life depends on their composition. For example, their properties of the brass mixture of the copper and zinc are quite different from those of the German silver mixture of the copper, zinc and nickel, or bronze mixture of the copper and tin. 1 part per million ppm of fluoride ions in water prevents tooth decay, while 1.5 ppm causes the tooth to become mottled, and high concentration of fluoride ions can be poisonous. For example, sodium fluoride is used in the rat poison. Intravenous injections are always dissolved in water containing salts at a particular ionic concentrations that match with the blood plasma concentrations and so on. In this unit, we will consider mostly liquid solutions and their formations. This will be followed by studying the properties of the solutions like vapor pressure and colligative properties. We will begin with the pressure types of solutions and then various alternatives in which concentrations of a solute can be expressed in which liquid solutions. Then 2.1 Types of solutions. Solutions are homogeneous mixtures of two or more than two components. By homogeneous mixture, we mean that its composition and properties are uniform throughout the mixture. Generally, the component that is present in the largest quantity is known as solvent. Solvent determines the physical state in which the solution exists. One or more components present in the solution other than the solvent are called the solutes. In this unit, we shall consider only binary solutions, that is, consisting of two components. Here, each component may be solid, liquid, or in gaseous state and are summarized in Table 2.1. Table 2.1 shows types of solutions. Types of solutions. Gaseous solution, solute, gas, liquid, solid, then solvent, gas, gas, gas. Common examples: mixture of oxygen and nitrogen gases, chloroform mixed with nitrogen gases, camphor in the nitrogen gases. Then liquid solution, the solutes are gas, liquid, solid, and solvent, liquid, liquid, liquid. Common example: oxygen dissolves in water, ethanol dissolves in water, glucose dissolves in water. Solid solutions: gas, liquid, solid, 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 solid. Solutions of hydrogen in palladium, amalgam of mercury with the sodium, copper dissolved in the gold. 2.2 Expressing concentrations of the solution. Composition of a solution can be described by expressing its concentration. The latter can be expressed either quantitatively or qualitatively. For example, qualitatively, we can say that the solutions is dilute, that is relatively very small quantity of solute, or it is concentrated, that is relatively very large quantity of the solute. But in real life, these kinds of description can add a lot of confusions, and thus the need for a quantitative description of the solution. There are several ways by which we can describe the concentration of the solutions quantitatively. One is mass percentage, W by W. The mass percentage of a component of a solution is defined as mass percent of a solid component is equal to mass of the component in the solution by total mass of the solute into 100. For example, if a solution is described by 10% glucose in water by mass, it means that 10 gram of glucose is dissolved in 90 gram of water, resulting in a 100 gram solution. Concentration described by mass percentage is commonly used in industrial chemical application. For example, commercial bleaching solution contains 3.62 mass percentage of sodium hypochlorite in water. Volume percentage, V by V. The volume percentage is defined as volume percent of the component is equal to volume of the component by total volume of the solution into 100, 2.2. For example, 10% ethanol solution is water means that 10 ml of ethanol is dissolved in water such that the total volume of the solution is 100 ml. Solutions containing liquids are commonly expressed in this unit. For example, a 35% V by V solution of ethylene glycol or antifreeze is used in the cars for cooling the engine. At the concentration, the antifreeze lowers the freezing point of water to 255.4 K, that is minus 17.6 degrees Celsius. 3. Mass by volume percentage, W by V. Another unit which is commonly used in the medicine and pharmacy is mass by volume percentage. It is mass of the solute dissolved in 100 ml of the solution. 4. Parts per million. When a solute is present in trace quantities, it is convenient to express concentration in parts per million, ppm, and is defined as parts per million is equal to number of parts of the component by total number of parts of all components of the solution into 10 to the power 6. Equation 2.3. As in the case of the percentage, concentration in parts per million can be expressed as mass to mass, volume by volume, and volume to mass. A liter of sea water which weighs 1030 gram contains about 6 into 10 to the power minus 3 gram of dissolved oxygen O2. Such a small concentration is also expressed as 5.8 gram per 10 to the power 6 gram, 5.8 ppm of the sea water. The concentration of the pollutants in water or atmosphere is often expressed in terms of mu g ml to the power inverse or ppm. 5. Mole fraction. Commonly used symbol for mole fraction is X, and subscript used on the right hand side of the X denotes the component that is defined as mole fraction of a component equals to number of moles of the components by total number of moles of all the components. 2.4. For example, in a binary mixture, if the number of moles of A and B are Na and Nb respectively, the mole fractions of A will be Xa is equal to Na by Na plus Nb. 2.5. For example, solution containing I number of components, we have xi equals to ni by n1 plus n2 plus n3 plus ni equals to ni by summation of ni. It can be shown that in a given solution, sum of all the mole fractions is unity, that is x1 plus x2 plus plus x1 equals to 1. Mole fraction unit is very useful in relating some physical properties of solutions, say vapor pressure, with the concentration of the solution, and quite useful in describing the calculations involving gas mixtures. Example 2.1. Calculate the mole fraction of the ethylene glycol C2H6O2 in a solution containing 20% of the C2H6O2 by mass. Please read the solution given in your textbook. 6. Molarity. Molarity M is defined as number of moles of solute dissolved in 1 liter or 1 cubic decimeter of solution. Molarity equals to moles of the solute, volume of this by volume solution in liter. For example, 0.25 mole liter inverse or 0.25 moles solution of NaOH means that 0.25 mole of NaOH has been dissolved in 1 liter or 1 cubic decimeter. Example 2.2. Calculate the molality of the solution containing 5 gram of NaOH in 450 ml solution. Solution is given in your textbook. Please read that. 7. Molarity. Molality M is defined as the number of moles of the solute per kilogram kg of the solvent and is expressed as molality M equals to moles of solute by mass of solvent in kg 2.9. For example, 1.00 mole per kg or 1.00 mole solution of KCl means that 1 mole 7.4.5 gram of KCl is dissolved in 1 kg of water. Each method of expressing concentration of the solution has its own merits and demerits. Mass percentage, ppm, mole fraction and molality are independent of temperature, whereas molarity is a function of temperature. It thus is because volume depends on temperature and the mass does not. Example 2.3 is given in your textbook. Please read that. Solubility. Solubility of a substance is its maximum amount that can be dissolved in a specified amount of solvent at a specified temperature. It depends upon the nature of the solute and solvent as well as the temperature and pressure. Let us consider the effect of these factors in solution of a solid or a gas in a liquid. 2.3.1 Solubility of a solid in a liquid. Every solid does not dissolve in a given liquid. While sodium chloride and sugar dissolve readily in water, naphthalene and anthracene do not. On the other hand, naphthalene and anthracene dissolve readily in the benzene, but sodium chloride and sugar do not. It is observed that polar solutes dissolve in polar solvents and non-polar solutes in the non-polar solvents. In general, a solute dissolves in a solvent if the intermolecular interactions are similar in the two, or we may say like dissolves like. When a solid solute is added to the solvent, some solute dissolves and its concentration increases in the solution. This process is known as dissolution. Some solute particle in solution collide with the solid solute particle and get separated out of the solution. This process is known as crystallization. A stage is reached when the two processes occurs at the same rate. Under such conditions, number of solute particles going into the solution will be equal to the solute particles separating out, and a state of dynamic equilibrium is reached. Solute plus solvent to form solution. At this stage, the concentration of a solute in solution will remain constant under the given condition, that is temperature and pressure. Similar process is followed when gases are dissolved in a liquid solvent such as solution, in which no more solute can be dissolved at the same temperature and pressure is called as a saturated solution. An unsaturated solution is one in which more solute can be dissolved at the same temperature. The solution which is in dynamic equilibrium with the undissolved solute is the saturated solutions and contains the maximum amount of solute dissolved in a given amount of solvent. Thus, the concentration of a solute in such a solution is its solubility. Earlier, we have observed that solubility of a substance into another depends on the nature of the substances. In addition to these variables, two other parameters, that is temperature and pressure, also control this phenomenon. Effects of temperature. The solubility of a solid in a liquid is significantly affected by temperature changes. Consider the equilibrium represented by equation 2.10. This being dynamic equilibrium must follow Le-Chatelier's principle. In general, if in a nearly saturated solution the dissolution process is endothermic, the solubility should increase with rise in the temperature, and if it is exothermic, the solubility should decrease. These trends are also observed experimentally. Then, effect of pressure. Pressure does not have any significant effect on the solubility of a solid in a liquid. It is so because solids and liquids are highly incompressible and practically remain unaffected by the changes in the pressure. 2.3.2 Solubility of a gas in a liquid. Many gases dissolve in a water. Oxygen dissolves only at a small extent in water. It is this dissolved oxygen which sustains all aquatic life. On the other hand, hydrogen chloride gas HCl is highly soluble in water. Solubility of the gas in liquid is greatly affected by pressure and temperature. The solubility of a gas increases with the increase of the pressure. For the lower part is for solutions of the gases in a solvent, consider our system as shown in figure 2.1a. The lower part is solution and the upper part is gaseous system at pressure P and temperature T. Assume this system to be in a state of dynamic equilibrium, that is, under these conditions, rate of the gaseous particles entering and leaving the solution phase is the same. Now increase the pressure over the solution phase by compressing the gas to a smaller volume. Figure 2.1b. This will increase the number of gaseous particles per unit volume over the solution and also the rate at which the gaseous particles are striking the surface of the solution to enter it. The solubility of a gas will increase until a new equilibrium is reached, resulting in an increase in the pressure of a gas above the solution, and thus its solubility increases. Henry was the first to give a quantitative relationship between pressure and solubility of a gas in a solvent, which is known as the Henry's law. The law states that at a constant temperature, the solubility of a gas in a liquid is directly proportional to the partial pressure of the gas present above the surface of the liquid or solution. Dalton, a contemporary of Henry, also concluded independently that solubility of a gas in a liquid solution is a function of the partial pressure of the gas. If we use the mole fraction of a gas in the solution as a measure of its solubility, then it can be said that the mole fraction of the gas in the solution is proportional to the partial pressure of the gas over the solution. The most commonly used form of Henry's law states that the partial pressure of the gas in vapor phase P is proportional to the mole fraction of the gas X in the solution and is expressed as P is equal to KHX 2.11. Here KH is the Henry's law constant. If we draw a graph between the partial pressure of the gas versus mole fraction of the gas in solutions, then we should get a plot of a type as shown in figure 2.2. Experimental result for the solubility of HCl gas in a cyclohexane at 293 Kelvin. The slope of the line is the Henry's law constant AKH that is shown in figure 2.2. It is obvious from the equation different gases have different KH values at the same temperature. Table 2.2 that suggests that KH is a function of the nature of the gas. It is obvious from the equation 2.11 that higher the value of KH at a given pressure, the lower is the solubility of the gas in the liquid. It can be seen from table 2.2 that KH values for both N2 and O2 increase with the increase of temperature, indicating that the solubility of the gas increases with the decrease of temperature. This is due to the reason that aquatic species are more comfortable in cold water rather than in the warm water. Table 2.2 shows values of the Henry's law constant for some selected gases in water. Example 2.4 is given in your notebook. Please see and do that. Henry's law finds several applications in industry and explains some biological phenomena. Notable among these are to increase the solubility of carbon dioxide in soft drinks and soda water, the bottle is sealed under high pressure. Scuba divers must cope with the high concentrations of the dissolved gases while breathing air at high pressure underwater. Increased pressure increases the solubility of atmospheric gas in blood. When the divers come towards the surface, the pressure gradually decreases. This releases the dissolved gases and leads to the formation of the bubbles of nitrogen in the blood. This blocks the capillaries and creates a medical condition known as the bends, which are painful and dangerous to life. To avoid bends as well as the toxic effect of the high concentration of the nitrogen in the blood, the tanks used by the scuba divers are filled with the air diluted with the helium 11.7% helium, 56.2% nitrogen and 32.1% oxygen. At high altitudes, the partial pressure of the oxygen is less than that at the ground level. This leads to low concentration of oxygen in the blood and tissue of the people living at high altitudes or climbers. Low blood oxygen causes climbers to become weak and unable to think clearly. Symptoms of a condition known as anoxia. Then, effect of temperature. Solubility of a gas in a liquid decreases with the rise in the temperature. When dissolved, the gaseous molecules are present in the liquid phase, and the process of dissolution can be considered similar to the condensation, and heat is evolved in this process. We have learnt in the last section that the dissolution process involves dynamic equilibrium and thus must follow Le Chatelier's principle. As dissociation is an exothermic process, the solubility should decrease with the increase of the temperature. In the next class, we will learn about the vapor pressure of the liquid solutions. So today it's up to this. If you like this, please like, share, comment and subscribe to my channel, and please share this video as much as possible to your friends. Thank you.